Hello everybody, I hope you're all doing well. We're going to solve a problem on 2D rigid body equilibrium again, but this time there is a small change in this. This is where we introduce the idea of a two-force member or a two-force body. Okay, let's first look at the problem itself. Okay, so I have two rigid bodies in this problem. Okay, so one of them is an L-shaped rigid body. Okay, I'm just going to draw that first here. Okay, this L-shaped rigid body, and this is supported in the following manner. First of all, at this point, there is a roller. Okay, so this roller I'm going to be drawing here. Let me fill it up. Okay, with some color or something here, and this is of course a circular roller. Okay, so this roller here is contacting the ground in the following manner. Okay, so if I draw the ground as such here, the roller is contacting the ground, and this roller here is an example of a situation where it allows you to move only within the rails as you are shown here. Okay, so these are the rails that the roller is supposed to move within. And then I also have the following. Okay, I have a spring which is attached at the other end of this L-shaped bar, as I'm going to be drawing here. Okay, so here is a spring, and this spring is attached to the wall right at the other end. Okay, all right. And then obviously, as you can see, right, if I have such a situation, then I know that okay, if I take this roller and then if I apply some kind of a rotation on this bar, this is not going to remain stationary, right? So in order to make it remain stationary, I'm going to take another bar. Let me draw it in a different color. So another bar, and this bar is going to be attached in the following manner. Okay, so here is the other bar. This bar is going to be pinned together with the L-shaped bar. Okay, so this is at the point B. Let me call this as the point B. Okay, so there is a pin there. Okay, they are pinned together, and then the end of this bar that is sticking out is attached by means of a pin to a wall. Okay, so this is another pin which I have shown here. Okay, now the body is in equilibrium, and here are the forces that I'm going to be placing on this body. So let me call this end of the bar as end A. Okay, then this is going to be called as the end C. Okay, the spring typically has a stiffness. Okay, so the stiffness of the spring, I'm going to just call it as K, and then we'll talk about that in a minute. And then this is the roller D. Okay, the roller is within a slot. Okay, so this is called as a bilateral constraint roller. Okay, or essentially a roller or a wheel within a slot. Okay, that's an example of what we have just drawn here. And then there are several forces that are acting on this body. Okay, these are the following forces. Let's say that there is a force here. I'm going to label them in a second. Okay, and then there is one more force that is acting right down here. Okay, and then there is another force that is acting vertically down here. And then there is also a couple moment that is acting in the following manner. Okay, so there is a couple moment that is applied on this body, and it is acting in the sense shown. Okay, I'm supposed to get this to be a little more circular, so I'm hoping that this will end up being a little more circular, but okay, that doesn't seem too great to me. So let me just draw it using my regular notation. Okay, apologies for that. All right, so here are my forces, and then I need to have some dimensions and so on. But first of all, the magnitude of these forces. Okay, so this is going to be a magnitude of 100 kilonewtons, kn kilonewtons. This is also 100 kilonewtons, and then this force is also 100 kilonewtons for me. Okay, and then I have the couple moment, which I'm going to say is a value of 200 kilonewton meters. Okay, so this is going to be 200 kilonewton meters. Okay, and then I need to have some dimensions, and the dimensions are the following. So starting from where these forces are applied all the way to where the point B is, and then I need to have a dimension all the way to where the point D is also sitting. Okay, let's say that the point D is here. This is the bar that is pinned to the roller. Okay, that's essentially what's happening, so that they can both move together within these rails that are provided. Okay, and then I have one more dimension starting from here, okay, all the way to where the force is acting, and then I have to have one more right there. Okay, so let me take this force creature and then say the value is given there, and then let's say, okay, these are the arrows here, distances will be given to me, and then one more down here. Okay, so there are actually 3 distances here. Sometimes my problems are not drawn to scale. I'm pretty sure you are aware of that by now. So these are dotted lines for me. These are also dotted lines for me. Okay, let me draw these as dotted lines as well. This is also a dotted line here. Okay, so let me make sure that's a dotted line, and this comes out right there, and so are these. Okay, so these are all the dimensions, and these dimensions are all equal to 1 meter. Okay, so this is 1 meter, this is also 1 meter, this is 1 meter, this is 1 meter, not drawn to scale, and this is also a distance of 1 meter. Okay, once again, what is the situation here? I have an L-shaped bar which is a CD. Okay, and this is attached to another bar AB by means of a pin at the point B. Okay, I need to find the reactions at pin A, pin B, and then at the roller D, and then at the point C, which is a spring. Okay, so this is a spring here. Let me just write it out. So this is a spring of stiffness K. Okay, at this point in time, I'm not interested in what the value of the stiffness is. Okay, so let me write down the problem here. Okay, so I have an L-shaped bar, which is this bar CD. Okay, is pinned to another bar AB at the point B. Okay, there is a roller constraint or roller support. Okay, so roller support at D and a spring at C, or spring support at C. Okay, and what do I need to find? All the reaction forces, or all support reactions at A, B, C, and D. Okay, so this is essentially the problem that we have here. Okay, so what am I going to do here? And this is something that I know from before. So we've solved enough problems now to realize that, okay, if I have a pin support in 2 dimensions, then I'm going to have 2 support reactions. If I have a roller support, then my support reaction is going to be normal to the direction of contact. Okay, and typically when I have a bilateral constraint, I'm going to assume that the contact is either on the top side or the bottom side. Okay, it does not matter which side it is, but I'm just going to assume it to be one or the other side. So there is going to be only one reaction force at D, and when we draw the free body diagram, we'll get to it. The first thing I'm going to do is, okay, I see that there are 2 rigid bodies, A, B, and C, D, so I'm going to have 2 free body diagrams. Okay, so solution. Okay, since we have 2 rigid bodies, this means that we need to draw 2 free body diagrams. Okay, Okay, let me just make sure that this 2 is written properly. Alright, so I'm going to draw the free body diagram, so which means that free body diagram of bar AB, and then also draw the free body diagram of the bar CD. Okay, so draw separately. Okay, so let us first draw the free body diagram of the bar AB. Okay, so let me start off with the bar AB. So start with the bar AB, and then here you'll see that there is a pin support, which means that we're going to have 2 reaction forces. Okay, then when I go to the bar CD, okay, bilateral constraint, bilateral roller support, we're going to assume the roller contacts the slot or the wall at either the top or the bottom surface of the wall. Which means that there is going to be one support reaction at the point D. Okay, so one support reaction at D in a direction that is normal to the contact. Okay, in a direction, that is normal or perpendicular to the line of contact. To the line of contact. Okay, and essentially we are also asked to neglect the size of the roller. Okay, so in a sense we can also neglect the diameter of the roller. Okay, neglect the roller dimensions. Okay, which means that this is considered to be very small. Okay, so that's also something that I will write here. So a couple of things. So I will start with the bar AB, and then at the bar CD I will see that this roller is contacting either the top surface or the bottom surface. So I'm just going to assume it to be contacting either the top or the bottom. That is an example of a bilateral roller support. Okay, and then I'm going to assume that the roller has roller diameter is negligible. Okay, and it's not something that is extremely necessary or so. Even if it has a diameter, it doesn't it shouldn't really bother us, but this is just for some kind of a simplification that will make the problem a little easier for me. Okay, all right, so let me start off by drawing the free body diagrams. So let me draw both the bars side by side. Okay, so here I have first of all the bar BC or AB, I'm sorry. So here is the bar AB. Okay, and then I have the bar CD, which is drawn in a different color, right, as you know. So here is the bar CD. So I start off with that piece, and then I come down here. Okay, and then I have this roller that I had drawn previously. Right, so here is the roller, and then the roller is of course pinned to the bar itself. Okay, and then I know that the line of contact is either the top or the bottom. Okay, so I'm just going to draw that as dotted lines. Okay, and as I said, you can say that either the contact is at the top surface or the contact is at the bottom surface. So you don't need to draw both of them. Okay, you don't need to draw the contact force at both the top and the bottom surface. It is going to be one or the other. Okay, and then I also have this spring, right? So let me draw the spring in this following manner. Okay, so here is the spring. Okay, so I'm just breaking the spring out at the point C, and I'm drawing it separately in the following manner. Okay, need to bring that there, and then here is the spring. Okay, and my intention is that, okay, I'm going to start off by looking at first of all the forces acting at several of these points. I know that the point B is right here, so this is the point B, this is the point A, so let me call that as point A, and then this is the point B. Okay, and then likewise the point B is also on this bar here. Okay, this is the roller at D. Okay, and then this is the point C, which means that this is also the point C. I'm just breaking out the spring and then drawing it as a separate entity. Okay, and then this is the wall that I see on the other end. Okay, let me start off by drawing first of all the reaction forces at the bar AB. I know that there is a pin here, which means that I'm going to have two support reactions. Okay, so I'm just going to assume the directions for these. Let me say that the reaction at the point B is pointing vertically up. Hopefully this is vertically up. Okay, I'm going to call it as by, and then I'm going to have another force that is drawn in the horizontal direction. Let me take this point here, and then this is horizontal. Okay, so this is going to be the force B suffix x. That's a pin. I have a pin at the point A, so I'm going to draw a force that is horizontal and a force that is vertical. Let me just make sure that these lines are indeed horizontal and vertical. Okay, so this is the point A, and then I'm drawing it in this particular manner. Let me move this guy a little here and then bring this creature right there. Okay, fantastic, I got it. Okay, so I'm going to call this as AX, and then I'm going to call this as AY. Okay, and then one thing that I forgot to give you at the beginning of the problem is the dimensions for these bars. Okay, for AB at least. So for AB, the dimensions are the following. Okay, this is going to be a slope triangle that is given to me. Okay, so which means that essentially I have a slope triangle, and this slope triangle is the following form. Okay, this is going to be a 3 4 5 slope triangle. So this is 5, this is 3, and then this is 4. Okay, so I'm going to bring that slope triangle right down here. So that's a 3 4 5 slope triangle. What does it do for me? So this is 3 4 and then 5. This essentially tells me that the dimensions of this bar AB are scaled in the same manner, which means that I can say, hey, distance from point B to point A is going to be a distance of 4 meters. Okay, let me extend this probably fully here, and so this is going to be 4 meters, and the height from point B to point A is going to be 3 meters, as you might have guessed. Okay, so this is going to be 3 meters. So let me write that out as well, and then of course these are all going to be my dotted lines. So, once I have the free body diagram drawn, right, then pretty much the problem is more or less just math. Okay, there is not much to do with it does not have much to do with statics as such. Okay, so I have this diagram done. Now comes a couple of important things. Okay, I just want to take this bar here and make sure that I give enough space between the two. Now, very important thing, look at this point B here and then this point B here. If I assume that the forces Bx and By are pointing in the following manner on bar B, then these forces should be equal and opposite at the point B on this bar here. Okay, this is because they're joined together, right? So if I'm trying to separate them out, I'm going to make use of Newton's law of action and reaction. So if I assume Bx and By to be the action forces, the reaction force on this point B should be equal and opposite. Okay, so please always be careful that you're drawing them this way. So this is going to be the force Bx. Okay, and then I'm going to have the force By, which is acting vertically down. Okay, so this is going to be the force B suffix Y. Then what else do I have? I have a spring. I'm going to assume that the spring is in a state of tension. okay, which means that the spring force at this spring is going to be pointing in this particular direction here. So this is going to be the force Fs, which is the spring force. Okay, I'm going to call this as the stiffness of the spring. Now notice that this point C on the bar was attached to that point C on the spring, which means that at this point C I'm going to have an equal and opposite spring force, as you can see, right? Exactly what we did for the point B on the bar BCD. Okay, so that's the point B that is labeled there. And then the roller reaction. Okay, the roller reaction is either pointing in or out. I mean, it's pointing either vertically up or vertically down. Depends on what you want to choose as the contact. Okay, so it can either just be one or the other. Or a nicer way, an even better way is the following. Okay, I will take this roller and then remove it out of here. Look at this. I'm going to take this roller and then remove it out of here. Okay, and then here is what is going to happen. Okay, hey, this roller is contacting the top or the bottom surface, right? I'm going to take this guy and then put that here. I'm going to take that guy and then put that here. Okay, so this was the actual free body diagram of the roller itself, as you can see. Okay, and what is going to happen, the roller is contacting the ground, which means that there is going to be a reaction force from the ground on the roller or the wall on the roller. So this is the reaction of the wall, but then the roller was pinned at this particular point to the bar, which means that there is going to be a reaction force from the roller which is going to be pointing vertically down. Okay, so this is going to be the normal force at D, which means that at the point D on the bar I'm going to have an equal and opposite normal force, as you can see. Okay, so this is going to be the normal force ND. Okay, so this is the free body diagram of the roller. Okay, so this is FBD of the roller. Okay, this is the FBD of bar AB. Okay, then this is the free body diagram of the spring. And of course, I'm not yet done with the free body diagram of this bar CD because I have other forces acting on it. So here are the forces that are acting on it, as I'm going to be drawing in a second. So there's one force here, and then there is another force which is acting down here. Okay, and then there is a force that is acting vertically down right there, and then I'm also going to have a couple moment that was acting in the direction that is drawn. Okay, and these are all the forces here. This is 100 kilonewtons, 100 kilonewtons, 100 kilonewtons. This is 200 kilonewton meters. That is the couple moment. Okay, and then I have the dimensions as well for these things. Here are the dimensions. Okay, so that one will be taken care of in a minute. Then I have this contact here. This is of course not drawn to scale, as you know very well by now. Okay, with most of my drawings. I'm trying my best, of course. I hope that you see that too. Okay, so these are all dotted lines. Okay, and then I have a set of dimensions right on the top here as well. I'm just going to write it as 1 meter. Okay, so as you will see, this distance is 1 meter. This distance is also 1 meter. This is a distance of 1 meter, 1 meter, and then a distance of 1 meter here. Okay. And of course, I'm ignoring the dimension of the roller. It does not make any huge difference to my life. Okay, and this is going to be the free body diagram of the bar CD. Okay, so I have drawn several free body diagrams now. I decided to draw only that of A, B, and CD, but then in the meantime, I thought, okay, why not, draw the other things as well. So this is the free body diagram of the roller. As you can see here, the roller is contacting the wall, which means there is going to be a wall reaction either at the top or the bottom side of this contact. I'm assuming that there is only one contact side at a given instant in time. So the wall reaction is pointing this way. The roller is going to have an equal and opposite force at the pinned point here, which means that there's going to be an equal and opposite force back on the point D. Likewise, I have a pin reaction at point B on this bar BA. Okay, which means that I have to have an equal and opposite reaction force at the point B on the bar CD. Okay, and then I also have the free body diagram of the spring that was drawn here, and then this is lastly the free body diagram of the bar AB. Okay, so we have broken this problem into all these several pieces. What am I going to do with it? I'm first going to take this bar AB, okay, and then I'm going to bring it down. the free body diagram of this bar AB. So I'm going to analyze this first by summing forces and then summing moments. Okay, so I'm going to say, okay, and for all of this I have to have a coordinate frame which has to be drawn. So let me draw that somewhere here. Okay, so some kind of a coordinate frame where I say, okay, this is positive x, positive y, and then counterclockwise rotations. Okay, this is positive y, this is positive x, and then counterclockwise rotations. Okay, all right, I come down here and then I say, okay, I have the free body diagram of AB. What am I going to do? I'm going to first sum forces up. Okay, sum of forces in the x direction is equal to 0. What are my forces? I'm going to have AX and BX as the only forces. So this is going to give me AX is equal to BX. Then I sum forces in the Y direction and I set them equal to 0, and then I realize that, okay, there are only two forces, and I end up getting AY is equal to BY. And then I also do one more thing. Okay, I take this bar and then I sum moments about any point. Okay, so let me sum moments about the point A and set that equal to 0. Okay, counterclockwise rotations are positive, so you will see that I'm going to have BX. If I do the moment, it's going to be BX times the distance of 3. Okay, so that's going to be BX times 3, and then BY, if you do the right hand rule, it's going to be a counterclockwise rotation, so that's going to be minus BY times 4. That's equal to 0. Okay, so which essentially tells me the following. Okay, so BY and BX are related to each other. Okay, so our BX, I'm going to say, is 4/3 BY. Okay, and we also have that AX is equal to BX, which is equal to 4/3 BY, and then AY is equal to BY. Okay, what am I going to do with all this? Now look at this. Okay, so the resultant force at point B, I'm just going to call it as the force FB. Okay, so this is going to be what? It's going to be the square of the components, and then I take the square root of that, right? So which means that if I look at the resultant force, FB is going to be, BX is going to be 4/3 BY whole square, BY square whole to the power 1/2. Okay, or you would end up getting this as FB. BY square is a common factor, so I just take that out of the mix, and then this is 16/9 plus 1 to the power 1/2, or I will end up getting FB is equal to 5/3 BY. Or I have the following. Okay, this is going to end up really nicely. This tells me that BY is going to be 3/5 FB, which means that BX, which is going to be 4/3 BY, will end up being 4/5 FB. Okay, what is the significance of this? And of course, I know I have the other things as well, right? So AX is equal to BX, which means that this is also going to be 4/5 FB, and then AY is equal to BY. This is going to be 3/5 FB. Now the significance of this is quite nice, is because of the following fact. If I take the free body diagram once again, okay, so I'm just going to bring this guy here once again. I'm just going to copy that, and I'm going to clean up some of these things here. We know that this is the free body diagram, of course, and I'm going to clean up all of that. Okay, I don't need that. I don't need any of that either. I'm going to get rid of that. I'm going to try and get rid of that guy. Alright, beautiful. Alright, so here is what I have. Then here is the point B. Okay, this point B, let me mark it down here. Let me take this point A, and then let me mark it down here. Okay, now watch this. I found out that BX and BY are related to the resultant force FB by making use of 4/5 and 3/5 ratios, which means that if I draw the force FB, it's going to be pointing in the following manner. This is the resultant force B. Okay, And if I draw a slope triangle now, okay, for this force FB, it is going to end up being the following. What do you know? The slope triangle is going to be the same as the slope triangle there. So this is going to be 3, 4, and 5. And of course, you'll see that at the point A, the force there is also the same force. Okay, this is going to be the force FB as well. And the slope triangle here is also going to be the same thing. Okay, because I know that this is also going to be 3, this is going to be 4, and this is going to be 5. And so this is very nice right here. I mean, of course, these are going to be in the same direction. So let me just make sure they indeed do look in the same direction. Now here is what I'm seeing. This bar AB is a two force member because you see there are forces at only 2 points on this body. Okay, there is a force at point A, there is a force at point B. These forces are equal in magnitude because this force is also FB, this force is also FB, and they are opposite in direction. As you can see, this force is pointing away from B, this force is pointing away from A, and they are collinear. That is, if I join them together, they are along the same straight line, as you can see. Okay, so they are collinear, or they are along the same straight line, and such a body is called as a two-force body or a two-force member. Okay, and instead of calling this as FB, I'm just going to call this as FAB because it pertains to the body AB. Okay, so I'm just going to call this as FAB. Okay, to just call this as FAB. It is just a name, right? What is in a name? I can call it as FB, or I can just call it as some reaction R. Okay, but the key idea is this. Okay, so on the bar AB, okay, there are forces at only 2 points on the body, that is points A and B. Okay, as you can see, the force at A and B are equal in magnitude, and opposite in direction. And the important thing is the force at A and B are collinear. That is, they share the same line of action. As you can see, right, they share the same line of action. And what do you know? This line of action is given by joining the points A and B. Okay, and the line of action of the force at A and B is given by joining the 2 points A and B. Such a body is called as a two-force body or a two-force member. Okay, so such a body is called as a two-force body or a two-force member. Okay, this is a key idea. And why is this useful is because if I recognize a two-force member, then all I have to do is I just draw forces at the 2 points, equal in magnitude, opposite in direction, and sharing the same line of action. Okay, so the idea is this. Okay, so which means that if we can recognize a body as a two-force member, we can then draw the force on the body to be equal and opposite at the 2 points and sharing the same line of action and having the line of action given by joining the 2 points. Okay, so moral of the story is that if I have a situation, I go back to my figure and I'll come back to my write-up again. Okay, if I go to my figure, I see that, okay, there are forces at only 2 points, A and B. What do I know about these forces? I know that these forces are equal in magnitude. Of course, I need to reduce the length of that line here. I just recognize that. I know that these two forces are equal in magnitude because one is FB, the other is FB. I just call them as FAB. It makes no difference, okay? They are opposite in direction, as you can obviously see, and then they have the same line of action, okay? If I take the line of action of this force and I extend it, it's just going to pass through the line of action of the other force. So such a body is called as a two-force body. So this is a two-force member. Okay, so which means that instead of this force Bx and By, I can just say that there is a force Fb or Fab, and Bx is nothing but 3/5 Fb, and then By is nothing but 4/5 Fb. Okay, so this is going to be 3/5 Fab, and then this is going to be 4/5 Fab. Likewise, Ax is going to be 4/5 Fab. And Ay is going to be 3/5 Fab. Okay, so this is the idea of a two-force member or a two-force body. Okay, and so typically there are only forces at 2 points on the body. Okay, forces at only 2 points on the body. There will be no couple moments acting. Okay, if you have a couple moment acting along with the force, then end of the story. That's not a two-force member. Okay, so I just maybe want to make a note of that as I go down. The forces are equal in magnitude, opposite in direction. They're collinear, or they're along the same line. Okay, and then the line of action is given by joining the 2 points. Okay, and if a body has so side note, if body has a couple moment on it, apart from forces at 2 points, it is not a two-force member. And why is that so? Is because, okay, where is a couple moment coming from? Couple moment is because of a couple. What's a couple? Two forces. Which means that if I had to have a couple moment, then I had to have had two other forces which were acting on this body. Which means in total I'm going to have forces acting at more than 2 points if I have a couple moment. Which means that it's not a two-force member. Okay, so if I have a couple moment, on top of forces at 2 points on a body, this implies that we have forces at more than 2 points on the body. Which means it's no longer a two-force member. Okay, so I hope this makes sense. Alright, so we are now done with the free body diagram of AB. I'm just going to go to the free body diagram of CD. Okay, I'm just going to go up and then get that free body diagram. So let's go up and grab that guy. So here is the free body diagram. Take all of that. Okay. I'm going to copy that and I'm going to bring it onto the next page right down here. Okay, so I'm just going to bring that down here. That's a fairly reasonable place to put it. I'll get rid of this so that maybe I can scoot this down onto the further to my left. Okay, so I'm just going to bring that down here. All right, fantastic. Now, what do I know from before? I know that, okay, this force Bx, as I have seen from before, I know that this Bx and By can be replaced by a single force. So I'm just going to draw that force here and say, okay, that force is going to be the same force which I had on the bar AB. Excuse me. So this is going to be FAB. Okay, and then I know that this is going to have the same slope triangle as before. Okay, so which means that I essentially have Bx is going to be 4/5 FAB, and then By, okay, this is going to be 3/5 FAB. Okay, and then my slope triangle is going to be the same as before. Okay, so this is going to be 4, 3, and then 5. Okay, all right. So now we are ready to solve this problem, because as you see, in total there are only 3 unknowns on this bar CD. Okay, so only 3 unknowns on CD. What are the unknowns? FAB, okay, then I have the spring force Fs, and then I have the normal reaction at the roller N suffix D. Okay, so that's a key point that we have. Now we have simplified the problem based on the fact that AB was a 2-force member. Okay, what am I going to do in this problem? I'm going to start off by summing moments. Okay, so one way I can do this is by summing moments. Let me call this point as some point E. Okay, just to label it. Okay, and nothing special about that particular point. I mean, there was nothing going on at that particular point. I'm just going to sum moments at the point E. I could also do the sum of moments at the point B. That is also completely okay with me. Okay, but let me do it at the point E. Okay, so sum of moments at the point E is equal to 0. Okay, or I could also do sum of moments at the point B is equal to 0. I can sum moments about any point of my choice. Okay, I'm just going to put a note right there. Okay, if I sum moments about the point E, I will see the following. Look at the spring force Fs is passing through the point E, so does not have any rotation about that point. Then look at the force ND. ND is passing through the point E, does not have any moment about that point. By, which is 3/5 FAB, is passing through the point E, does not have any rotation about that point. What else do I have? I have the following. The 200 kilonewton force. That's a couple moment, right? So I have to throw that into the mix. Okay, that's something that I have to do. So that's minus 200 kilonewton meters. So let me start writing that out. Maybe I need a little more space here, so let me scoot that down here. So that's minus 200 kilonewton meters. That's a couple moment. That's in the clockwise direction. Then what else do I have? I have Bx times the distance of 1 meter counterclockwise. Okay, so that's going to be plus 4/5 FAB times the distance of 1 meter. Okay, that's going to be in the counterclockwise direction. Okay, then what else do I have? The 100 kilonewton force, which is pointing vertically down, is going to cause a rotation in the counterclockwise direction. So minus 100 times 1, that is this vertically drawn force. Then I have to take a look at this other force of 100 kilonewton. This force of 100 kilonewton is not going to cause any moment for me. The spring force Fs is not going to cause any moment for me. Nd is not causing a moment, and then By is also not causing a moment, because all of them are passing through the point E. The other one is 100 times 2, which is clockwise. Okay, counterclockwise, I'm sorry, 100 times 2. So all of them put together, that's equal to 0 here. Okay, then if I solve for FAB, then I end up getting FAB is equal to 125 kilonewtons. Okay, so this is the reaction. And then I also know that, okay, hey, this means that Bx is known to me. This was 4/5 FAB. Okay, and By is also known to me. So this is 4/5 of 125. So that's 4 by 5 times 125, and then this is 25 times 5 is 125. So this is going to be 100 kilonewtons. Okay, and then By is going to be 3/5 FAB. Okay, so which means that this is going to be 25 times 3, which is 75 kilonewtons. Okay, and I know from the free body diagram of AB, I know that AX is equal to BX, so this is going to be 100 kilonewtons. AY is equal to BY is going to be 75 kilonewtons. I got a positive sign, which means that the direction I chose was okay. Okay, so obtain a positive sign for FAB, which means we chose the right direction for FAB. If we get a negative sign, it is not a problem. If we had ended up getting FAB to be negative, it is not an issue. Okay, because we don't know what the direction is to begin with. So how am I supposed to second guess this with all the so many forces acting on this body, right? Okay, so that's about it. And then I have a couple more things to do, right? I have to sum forces in the x and the y directions on the bar CD. Forces in the x direction, I set them equal to 0. What are my forces? Bx is pointing to the right, Fs is pointing to the right, the 100 kilonewtons and the other 100 kilonewtons is also pointing to the right. Okay, so here are my forces. I'm going to have Bx plus Fs plus 100 plus 100 is equal to 0, which means that Fs is going to be minus 300 kilonewton. Okay, so once again, okay, I'm just going to underline some of my answers here. Okay, so this is something that we know, this is something that we found out, and then here FAB. Okay, so the spring force is negative. Obtain Fs to be negative. Okay, we had said spring was in tension when starting the problem to begin with, which essentially says that we chose the wrong direction for the spring force. So we now know spring is in compression. Because we get a negative sign, the direction of that force is opposite to what we thought it was. Okay, and then lastly, we also have to find out the roller reaction. That's by summing forces in the vertical direction. Okay, so what are my forces here? I'm going to have ND. Okay, so I just don't want to make that is, I want to get rid of all of these guys. Okay, I just marked them so that to show you that they were not causing any moments about the point E. So let me get rid of the tick marks on these things. Okay, so if I sum forces in the vertical direction, I'm going to have ND, then I'm going to have the other force, which is BY, which is pointing vertically down. Okay, so those are the only two forces, and then I have the 100 kilonewton force also, of course, which is pointing vertically down. So let me scoot that in. So this is going to be N suffix D minus 100 minus by. This is equal to 0, which means that N suffix D is going to be 175 kilonewtons. Okay, and so we have found out all the unknowns in this problem. So the major idea of this problem is the following. Okay, the major idea of the problem is that okay, if I go back to my free body diagram of the bar AB as I have drawn here, this is a two force member. If it's a two force member, what is the consequence? It means that there are forces acting at only 2 points on the body. So when I look at the figure, I immediately recognize and see, okay, hey, there are forces acting at only 2 points. These forces are equal in magnitude, as I have drawn here. They're opposite in direction, and they're collinear. Collinear meaning that they are along the same straight line, or their line of action is the same. Okay, So that's something I want to mark here. So they're collinear here, which means that they have the same line of action. And how do you get this line of action? The line of action is obtained by joining the 2 points A and B. It's as simple as that. So anytime I recognize that I have a body that's a two force member, I will find out, okay, hey, this is the direction of the force on that body and it's the same force at the 2 points. So I don't need to perform any extra equations for that body. I can directly move on to the next one, okay, making use of information from this body. So that is the highlight of this particular problem. Okay, and then I'm going to solve one more problem of this nature, as you will see in the next video. All right, take care all of you, and stay safe. And very last second is that, okay, there is lots of things going on in this problem. There is a spring, there is a roller, then this is a two force body. So try to solve this problem at your own pace, and then try to understand how we got the different facets of these support reactions. Okay, take care. Bye bye.